Okay, we are on time. Let me introduce now Luciano, if I say it correctly.
Yes, it's
about sparse temporal spanners, and I'm looking forward to your talk.
okay. Thank you for the introduction. This is a paper we have presented last year at ESA. This is a joint work with a bunch of friends from different parts of Italy. Let me just say that Davide below is also here. He's the guy who gave the previous talk. Okay, this paper is about spanners in temporal graphs. I know you are all experts in temporal graphs, so you know that there are a lot of models. We adopt a really simple one in which a temporal graph is just a graph with time labels on the edges. And for instance, the time label, this defines the time instant in which the label is available. For instance, this guy is available at time 1, and this guy is available at time 6 and time 10. But for the sake of simplicity, let me just assume that we have just a single time label on for each age. Okay, so given this simple temporal graph, a really important notion is that of temporal path from a vertex U to a vertex V, which is a UV path in which with non-decreasing time labels. For instance, here, the blue path is a temporal path from U to V with time labels 3 and then 4. And when there is such a path, we say that U is temporally connected to V. Okay? The problem we are interested in is a problem introduced by Kempe et al. In a Stock paper some years ago, that asks for sparsifying and given temporal graph while maintaining temporal connectivity. And this problem can be formalized by introducing the notion of temporal spanner, which formally is a subgraph H of the temporal graph G that preserves pairwise temporal connectivity. And what the goal is to find good temporal spanners that are spanners with small sides, and the sides measured in terms of number of edges of the graph subgraph H. Okay, this is a starting problem, and what is known for this problem? We have a bad news. This is a result by Axiotis and Fotakis, and they prove that essentially, if you have a general temporal graph, you can hope for sparsifying it in general. That more formally, they built a temporal graph, a dense temporal graph with theta of n square edges that essentially cannot be sparsified in the sense that any temporal spanner must have sides omega of n square. Okay, this is the bad news. But if actually your temporal graph is actually clique, then we have a good news. And this is a paper by Castell et al. And they prove that any temporal clique admits a sparse spanner of sides omega of n log n edges. Okay. Okay, this is our starting point. Let me point out that this construction here only preserves temporal connectivity between pair of vertices. That means that it ensures that for any pair of vertices, there is a temporal path in the spanner, but there is no guarantee on how long this path is. So we want to provide a better guarantee. That means that we introduce a stronger notion of spanner, which is a spanner with stretch alpha, or a temporal alpha spanner, that essentially is a subgraph that approximately preserves distances between pair of vertices other than temporal connectivity. And more formally, it's a subgraph H in which for every pair of vertices U and V, you have that the distance in the spanner for U to V is at most alpha times the distance in the original graph from the same vertices, for the same vertices. Okay, but what do we mean for distance in a temporal graph? there are several natural ways to define the notion of shortest path and so distances. This is a few, the most common ones. And for instance, a temporal path could be defined to be a shortest path if it minimizes its length, defined in terms of edges, or it has minimum arrival time, or maximum departure time, or minimum travel time, which is defined to be the difference between the arrival time and the departure time. Okay, they are all naturals. In our paper, we mainly focus on this one. There are at least two reasons for that. The first reason we feel is the main one, is that this notion generalizes the standard notion of distance in static graph. Whenever you have a temporal graph where all the time labels are equal, essentially you have a static graph. In this case, this notion reduces to the standard notion of shortest path in such static graph. Okay, this is the main reason, but they rejected the paper by saying that we did not motivate enough our choice. So we also, in the next revision, we also addressed a bit the other notions or distances, and we provided a simple, strong lower bounds for that. So this is the second reason why you should focus on this one in order to get positive results. Okay, so our results, we have essentially three types of results. The first bunch of results concern temporal clicks. We want to understand for temporal clicks which kind of stretch trade-offs can be obtained for a temporal click. And any trade-off can be seen as a point in a plane where the x coordinate represents the stretch and the y coordinate represents the size of the spanner. For instance, this point here is the spanner by Castet et al, with sides n log n and stretch roughly n minus 1, because they just preserve temporal connectivity but can have long path. We are able to show that other trade-offs are possible. For instance, we are able to prove that there is a spanner with stretch 3 and sides roughly n times square root of n. I will not care about polylogarithmic factor here, more or less. So we are able to prove this trade-off here, and we are able to prove that it's possible to compute a sparser spanner with stretch 5 and even sparser with stretch 7. And the general trade-off we are able to guarantee is this one. You can get stretch 2k minus 1 with sides roughly k times n to the 1 plus 1 over k times polylogarithmic factor. Okay, and interesting enough, if we set k equal to log n, we have this spanner here that has stretch log n and almost linear sides. And I like it because this is just a log n factor away from this spanner by Castet et al, but it provides a much better stretch. Okay, and okay, this is the upper bound for the trade-off we are able to prove. We are also able to prove that 3 is the minimum stretch you can get in general for temporal clicks by showing a simple construction that show that if you want stretch strictly less than 3, that for clicks means 2, then you have a lower bound omega n square in the sides. Okay, this is the first type of our results. Let me move to the second bunch of results, which are for general graphs. And remember that for general graphs, the strong Axiotis and Fotakis lower bound applies. So we have to somehow restrict our problem. And in order to do so, we focus on the single source case, where we want to essentially approximately preserve distances from a given source vertex S to any other vertices in the graph, any other vertex in the graph. And for the single source case for general graph, we are able to prove that we can get stretch 1 plus epsilon for any positive epsilon with almost linear sides. And this upper bound is somehow tight in the sense that if you want stretch 1, that means exact distances, then you have to pay omega of n squared in the sides of the spanner. Okay, this is the second type of results. The last bunch of results concerns the role of lifetime. What is the lifetime? The lifetime is a parameter, I call it L. That is the number of distinct time labels in the graph. And this is a parameter ranging from 1 to roughly n squared. And I like this parameter because it's like a knob that controls somehow how temporal your temporal graph is. For instance, when you have lifetime 1, essentially you have a static graph, and every path here is temporal, and so that's a static graph essentially. When you when you want to consider a bit more complex temporal network, you can consider graphs with lifetime 2 and then lifetime 3 and so on. And when you reach lifetime theta of n, you can build a lower bound construction by Axiodis and Fotakis. Okay, and our question was, can we prove better trade-offs for graphs with small lifetime? And the answer is somehow yes. For clicks, we are able to show that if you consider lifetime 2, you can obtain stretch 2 with size n log n. But when you move from lifetime 2 to lifetime 3, then we have a lower bound of omega n squared, for stretch 2, but for stretch 3, we are able to obtain sides n log n. And this trade-off with stretch 3 and sides n log n is also achievable for any constant lifetime L. And this is for these results are for clicks. We have also a simple construction for general graphs, and they show that this simple construction that somehow links the static world to the temporal one. And the construction is the following, it claims the following. If you have an alpha spanner of a given size for static graphs, you can use this upper bound to build an alpha spanner for temporal graph with lifetime L, having sides the same size times the lifetime. And this is a simple construction, but it still provides interesting answers. For instance, if you focus, for instance, on the lifetime little o of n, you are able to prove that there is a temporal spanner with logarithmic stretch and non-trivial sides of little over n squared. And this is nice because when you move from lifetime little of n to theta of n, the Axiodis and Fotakis lower bound applies. That means that this lower bound essentially is using the asymptotically minimum value of lifetime. Okay, so this is the our results. Now let me move to the technical part of the talk, and I'd like to give you some intuition on how to construct such spanners for click. I will show you the rather simple construction for the 3 spanner of sides n times square root of n, and then I will give you some idea how to generalize it. Okay, how to build this spanner. Consider vertex U and look at all incident edges. Remember that we are in a click, so these are all the vertices in the graph. Okay, and order the edges according to the time labels, and we consider the first roughly square root of n edges. Let me call these edges red edges for simplicity. And at the beginning, our spanner is the union of all these red edges. Okay. Well, then for each vertex U, if you look at these red edges, they define a subset of vertices. this one. Let me call them this set S sub U. Now we collect all these sets, and we compute for these sets a knitting set here. Okay, and there is a technical lemma, well-known technical lemma that show you that since these sets are have sides at least square root of n, then the eating set, the size of the eating set is order of square root of n as well, up to polylogarithmic factor. Okay, and now so we have an eating set of sides roughly square root of n, and we want to use it, and we use it to compute a clustering for the vertices. How to do that? Essentially, for each element in the eating set, we build a cluster of vertices with this X will be the center of the cluster, and we put in this cluster all the vertices U such that X hits the corresponding S sub U. Okay, so this is a cluster with center X. Look at all the vertices in the cluster, order them with respect to time labels, and look at the rightmost vertex in the cluster that we call a special vertex Z. Okay, this would be a special vertex of this cluster. Of course, this vertex, it has its own red edges and all the other edges incident to it. Okay, and now the idea is to show you that if you want to go from the vertex U to vertex V, we can use the red edges plus at the other edges in order to get a temporal path from U to V of length at most 3. How to do that? For instance, if you want to go from U to V, look at the cluster containing U, and if V is, for instance, exactly the special vertex, here we can use this temporal path. And notice that this is temporal because of the ordering we choose here. Okay, then if V is not this guy here, then could be, for instance, a red neighbor of the special vertex. Now we cannot use this path because this is a red edge for Z, this is a red edge for Z, so we maybe the time label of this edge could be too small with respect to this one. But in this case, we use a direct edge for U to V, this blue edge here. And this blue edge is not in the spanner, actually, so we add it to the spanner. So we add all these blue edges here. How many blue edges we have? We have, this is roughly square root of n times the number of vertices. So we have still order of n times square root of n blue edges. And if V is in the last case, when V is not a red neighbor for the special vertex Z, then it means that V must appear here somehow. For instance, V could be this guy. In this case, we use this path. This must be temporal because since this is not a red edge for Z, but this is, for the ordering we use it to choose the red edges, then it must be that the time label, the green edge should be larger or equal to the time label this guy. And so this is a path of length 3. Again, we don't have actually the green edge in the spanner where we can add it. How many green edge? We have n green edges for every special vertex. The number of special vertices is square root of n. So we have, again, the number of green edges in total is order of n to the 3 over 2. And so this gives the spanner with stretch 3 and sides roughly n log n square root of n. Okay. And in order to generalize it to a larger stretch, with the idea, I'll just give you some idea. The idea is the following. Instead of now let me try to show you how to get stretch 5 with sides n to the 4 over 3. And the idea is, instead of considering the first square root of n red edges, we reduce the number of red edges to cube root of n, roughly. Now the number of red edges reduced to the bound we want, but the size of the thin set increases to this value. How to manage it? The idea now is the situation is this one. We have U, which is in a cluster with a special vertex. And now, for instance, we cannot add, now we have a lot of clusters, so a lot of special vertices. So we cannot, for instance, add all the green edges for every special vertex because they would be too much. So the idea is to consider for each special vertex to consider the next roughly n to the 2/3 edges. Let me call them purple edges. And now we can add these purple edges to the spanner, and the number of purple edges is the bound we want, because we have such many edges for each special vertex. Special vertices are roughly n to the 2/3, and so we have this number of purple edges. And now we can use these purple edges to define another collection of sets and compute a second level 18 set for them and the corresponding second level clustering. And now when you look at the entire situation, essentially you have this situation here. If you look at the vertex U, this U belongs to some cluster of the first level with center X and special vertex Z. Now Z belongs to a second level cluster with center Y, which is an element of the second 18 set. And this cluster contains special vertices from the level 1. And you can define as before a special vertex of these special vertices and the super special guy Z sub 2. Okay, and now if you want to go from U to V, you can use similar argument. If V is one of these two guys, you can use this path here. If V is belongs to one of these vertices, we add the direct edge. When V is here, we use this path, we add this blue edge. And when V is here, we can use this path and we add the green edges. And the idea is that similarly, the number of the edges you have to add is still roughly the bound n to the 4/3. And all these paths are essentially temporal. Okay, this is the idea. If you generalize it to a k-level hierarchical eating set and clustering, you get the general bound. Okay, so this concludes the technical part. Let me move to the last part, final one. And I would like to give you two selected open problems. The first one concerns cliques, temporal cliques. This is a problem really, it would be really nice to solve for me. For the stretch tree, I show you a reader sample construction of size n times square root of n, but we don't know if this construction is tight. And the main open problem here is to show, is it possible to find a tree spanner for a clique with size n times polylogarithmic factor, almost linear size, or it is possible to prove a lower bound of omega of n to the 1 plus epsilon? This would be really nice to know. Okay. Okay, this is the first open problem. The second, the last selected open problem I want to show you concerns the problem of going beyond the cliques, temporal cliques. As I mentioned before, from one side we have that for temporal cliques, now we have a lot of way to sparsify cliques. But for general graphs, we have a strong lower bound of omega n square in the sides, even for temporal connectivity. What there is in between, we don't know. And maybe a simple step forward, the general case would be that of considering n-2 regular graph instead of cliques. And it seems that even this case is not trivial, because according to us, we are not able to use the same techniques for cliques for solve this case. So maybe it can be a good problem to start with. Okay, so thank you for your attention. That's all.
Thank you very much, Luciano. Questions? From online? Maybe I ask something. So if I got it right,
Yeah.
you consider only non-strict temporal paths, right?
Yes.
What happens if you constrict strict?
For strict temporal paths, you have a strong, really simple, strong lower bound. Think of a clique where all time labels are 1. You cannot remove any edge.
Correct.
So you cannot essentially sparsify.
What happens if you? Okay, I have some questions. Let me think it more, and I can ask you in the break.
Thank you.
Okay. Thank you again.